Pressure relief valves are typically the device used to limit the maximum head created by a surge event. Pressure relief valves open and close at preset pipe pressures. They limit or crop the maximum head by dumping fluid to atmosphere, or to a nearby tank, or to the low head suction side of a pump. Pressure relief valves can be found in two formats: a spring-loaded mechanism balanced directly against the fluid pressure on the valve's gate or diaphragm, as shown here. These tend to be found on older designs. They are less compact and as a result can be more expensive than the more modern alternative. A hydraulically actuated valve, where the spring-loaded mechanisms are moved into compact pilot valves on a hydraulic servo circuit, and the servo circuit uses the difference in pressure across the valve to open or close the valve's gate or diaphragm. Surge anticipator valves are a special type of pressure relief valve. These valves anticipate when the valve will need to open and act as a pressure relief valve by firstly sensing a sudden drop in head, for example created by pump stop, and then opening after a preset time delay. Surge anticipator valves can be designed to anticipate the reflection of the high pressure wave after a pump stops, and be open, already reducing the head in the system before the return pressure wave arrives. Their ability to open early can lead to better outcomes than a simple pressure relief valve that only reacts to arrival of a high head. Surge anticipator valves will, however, make the minimum head worse. So be diligent in your analysis of systems with surge anticipator valves to make sure both the minimum and the maximum head outcomes are acceptable. Let me use the next few slides to emphasize that pressure relief valves treat the symptoms of excessive head. They can be an inexpensive and effective solution in the right circumstances. However, transient analysis needs to include the effects of pressure relief valve closure in the context of the prevailing system fluid velocities. In some situations, pressure relief valve closure can introduce an additional unacceptable transient event. This first slide demonstrates what we are often trying to do by using a pressure relief valve. Simply put, we are trying to crop off these unwanted peaks in head and keep the outcome below the pipeline's pressure rating. Here is another way of looking at that objective in a different pipeline. At the part of this pipeline that goes under the river, its pressure rating would be exceeded every time the inlet valve to the reservoir closes. Releasing water into the river through a pressure relief valve is an inexpensive solution, which we can see in this hydraulic grade line. It has limited the maximum head well. The message, however, is to not only look at head graphs and hydraulic grade lines when analysing pressure relief valves. Always cross-check the head outcomes against graphs of system and relief valve flow rates. Why, you ask? Because flow rates reveal what is happening with the system velocity changes, which are the cause of surge amplitudes. You should always check to make sure that the pressure relief valve is closing at a time when the underlying flows, their velocities in the system, have dropped to an acceptable level. If not, closure of the relief valve is likely to add to the amplitude seen in the system. The message is the same when using anti-vacuum valves to limit the minimum head in a system. How do we limit the minimum head possible in a system? Well, we can use a one-way surge tank, air valve, anti-vacuum valve, or air cushion. A one-way surge tank limits the minimum head by dumping fluid at low head into the pipeline. They are typically connected to the main pipeline by a non-return valve to isolate the surge tank from the system during normal operations. When they need to be refilled, this is done through an altitude control valve or float valve connected to the main pipeline, or a totally separate fluid supply. One-way surge tanks may be a good solution on long effluent pipelines or raw processed water pipelines. They tend to be an undesirable solution on drinking water systems because water can stay dormant in the one-way surge tank for a very long time and can be a breeding ground for pathogenic microorganisms. Then a critical transient event occurs and the one-way surge tank inoculates the drinking water pipeline with these pathogens. Air valves and anti-vacuum valves limit the minimum head by dumping air into the pipeline. When the fluid pressure rises again at an air valve location, air valves tend to close without causing grossly significant pressure transients of their own. When the fluid pressure rises again at an anti-vacuum valve location, anti-vacuum valves can slam shut and create damaging pressure transients of their own, unless the anti-vacuum valve incorporates a slow closing mechanism. Air cushions are a device with an air valve on top of a storage canister. An air cushion limits the minimum head by dumping air into the canister. The purpose of the canister is to prevent air entering the main pipeline. An air cushion brings the added advantage of containing a confined volume of air when the water pressure rises again. This air becomes compressed and attenuates the surge before the air valve eventually releases the air into the atmosphere. How can a system configuration be reshaped in a way that reshapes the size of the surge problem or changes the location of the surge problem? Here are a couple of examples to think about. We could divide a very long pipeline into sections using non-return valves so that surge amplitudes in each pipe section are smaller than the surge heads that would occur if the whole pipeline responded as one fluid column. In a pumped drinking water system that has the choice to supply customers from a high tank or the pumps that refill the tank, instead of pumping through the customer reticulation pipe network, pump through a separate pumping main. On long pipelines across terrain with significant changes in land elevation profile, set control valves and pump stations in locations that enable the surge envelopes to best match the land profile. Allow me to close with this slide, which demonstrates how installing non-return valves very effectively limits the maximum heads experienced along most of this pipeline. We're looking at a 3.2 kilometre long pipeline with its hydraulic grade line and surge envelopes following pump power failure. The hydraulic grade line at 120 seconds after power failure is shown to make the separation of heads at the non-return valves evident in the bottom figure. The top figure shows the pipeline behaviour as a single segment. The maximum safe head is exceeded along most of the pipeline. The bottom figure shows the result of installing two non-return valves at 1 kilometre intervals back from the receiving tank. The entire pipeline remains within its maximum safe head. Segmentation works. Thanks for listening. Now please take a few moments to consolidate the key messages and review what you have learnt in this module.